Tonight we're going to talk about an object that physics says must eventually exist, but that the universe has never actually made. Not once. Across billions of galaxies and trillions of stars that have lived and died, this object has never formed anywhere. It's called a black dwarf. And it's not some exotic hypothetical. It's the inevitable final fate of the most common stellar corpse in the cosmos. Every white dwarf ever created is slowly, silently cooling, radiating the last of its heat into the void. And when that heat is finally gone, when the temperature drops to match the near absolute zero background of space, what remains is a black dwarf. Cold, dark, invisible. But the cooling takes so long that the universe itself isn't old enough to have finished the job. Not even close. Tonight we're going to find out why and what it means for the future of everything. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. There is an object in astrophysics that occupies a strange and almost paradoxical position. It is not controversial, it does not violate any known law of physics. Every mainstream model of stellar evolution agrees that it must eventually form. And yet, not a single one exists anywhere in the observable universe. Not orbiting any star, not drifting through any galaxy, not hiding in some dark corner of the cosmos, waiting to be found by a sharper telescope or a more sensitive detector. The object simply is not there. And the reason it is not there has nothing to do with our models being wrong. It is because the universe is too young. This object is called a black dwarf, and it represents the final, absolute endpoint of one of the most common stellar remnants in the cosmos, a type of dead star known as a white dwarf. Right now, scattered across the Milky Way alone, there are billions of white dwarfs. They are the dense, roughly Earth-sized remains of stars that have exhausted their fuel, still glowing faintly with the residual heat accumulated over billions of years of nuclear fusion. And they are cooling. Every single one of them is radiating its stored thermal energy into the vacuum of space, growing dimmer and dimmer with each passing age. When that process is finally complete, when the last trace of heat is gone and the surface temperature drops to match the near absolute zero background of the universe itself, what remains will be a black dwarf, a cold, dark, inert sphere of crystallized matter, invisible, silent, emitting nothing, reflecting almost nothing, the most permanent structure the cosmos can produce. But the cooling takes an almost inconceivable amount of time, not billions of years, not hundreds of billions. The timescales involved are so vast that they make the entire current age of the universe look like a single opening heartbeat in a life that will stretch for ages beyond counting. The universe is approximately 13.8 billion years old. The time required to cool a white dwarf into a black dwarf is measured in at least quadrillions of years. The universe would need to be tens of thousands of times older than it currently is for the very first black dwarf to appear. Physics guarantees this object will eventually exist, but the cosmos has not had remotely enough time to produce even one. To understand why, we need to understand what a white dwarf actually is, how it forms, and why its cooling is the slowest known process in all of stellar astrophysics. And to get there, we need to talk about stars. Every star you see in the night sky is a thermonuclear engine. Deep in its core, hydrogen atoms are being crushed together under immense gravitational pressure. Fusing into helium, and releasing enormous amounts of energy in the process. This is nuclear fusion, and it is what makes a star shine. The energy generated in the core pushes outward as radiation pressure, and this outward push is exactly what keeps the star from collapsing under its own gravity. A star, at its heart, is a balancing act. Gravity pulling inward, trying to crush the star into the smallest possible space. Radiation pushing outward, trying to blow it apart. For most of a star's life, these two forces exist in a state of equilibrium, and the star remains stable. Our Sun has been in this balanced state for about 4.6 billion years, and will continue burning steadily for roughly another 5 billion. During this phase, a star is said to be on the main sequence, a term astronomers use for the long, stable middle chapter of stellar life. Most of the stars you see in the night sky are main sequence stars. They are in the prime of their lives, steadily converting hydrogen into helium, shining with a brightness determined by their mass. But no fuel supply lasts forever. Eventually, a star begins to run out of hydrogen in its core. And what happens next depends almost entirely on one single factor: how massive the star is. This is one of the most elegant truths in all of astrophysics. A star's mass at birth essentially writes the entire script for its life and death. The mass determines how hot the core gets, how fast the fuel burns, how long the star lives, and most importantly for tonight, what it leaves behind when it dies. The most massive stars, those roughly 8 or more times the mass of the Sun, live fast and die violently. They burn through their hydrogen in just a few million years, a blink of an eye by cosmic standards. When the hydrogen fuel runs out, their cores are so hot and so dense that they begin fusing heavier and heavier elements. Helium fuses into carbon, carbon fuses into neon, neon into oxygen, oxygen into silicon, silicon into iron. The core builds up layers of successively heavier elements, like the layers of an onion, but iron is the end of the line. Fusing iron does not release energy, it absorbs it. When the core fills with iron, the energy source suddenly vanishes. The outward radiation pressure disappears, and within a fraction of a second, the core collapses under its own weight. The outer layers come crashing inward, bounce off the incompressibly dense core, and are blasted outward in a supernova, one of the most violent and luminous events in the entire universe. What remains at the center after this cataclysm is either a neutron star, an object so dense that a teaspoon of its material would weigh about 4 billion tons, or if the original star was massive enough, a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. But that is not our story tonight. Our story is about the other kind of star, the quieter kind. The kind that makes up roughly 97% of all the stars in the Milky Way. The kind that includes our own Sun. Stars with masses up to about 8 times the mass of the Sun follow a very different path when they die. They still run out of hydrogen in their cores. They still undergo dramatic transformations, but they never reach the temperatures and pressures needed to fuse elements all the way to iron. Their deaths are slower, less spectacular, and in a way, far more interesting for what they leave behind. When a star like the Sun exhausts the hydrogen in its core, the core contracts under gravity. This contraction heats the surrounding shell of hydrogen, which begins fusing in a ring around the now inert core. The extra energy causes the outer layers of the star to expand enormously. The star swells to many times its original size, becoming what astronomers call a red giant. Its surface cools as it expands, shifting from yellow-white to a deep, ruddy orange-red. But its overall luminosity increases dramatically because of the vastly larger surface area. The scale of this transformation is difficult to overstate. A star like the Sun, currently about 864,000 miles in diameter, will expand to roughly 100 to 200 times that size. Its outer edge will reach out to where the inner planets once orbited. When our Sun reaches this stage, roughly 5 billion years from now, it will swell to a diameter of perhaps 150 million miles or more. Mercury will be consumed. Venus will be consumed. Earth may or may not survive as a scorched, stripped cinder at the very edge of this bloated, dying star. But any oceans, atmosphere, and life will have been vaporized long before the red giant reaches its full extent. The surface temperature drops to perhaps 3,500 degrees Kelvin, cool by stellar standards, giving the star its deep red color. But the sheer size of it more than compensates. A red giant can be thousands of times more luminous than the same star was during its main sequence life. It is dimmer per square mile of surface, but there are so many more square miles that the total output soars. During the red giant phase, the core continues to contract and heat up. Eventually, it reaches temperatures of around 100 million degrees Kelvin, hot enough to begin fusing helium into carbon and oxygen. This helium fusion phase is shorter and more unstable than the hydrogen burning phase. Helium fusion proceeds through a process called the triple alpha process, where 3 helium nuclei combine to form 1 carbon nucleus. Some of that carbon then captures an additional helium nucleus to form oxygen. These 2 elements, carbon and oxygen, will become critically important later in our story. For stars in this mass range, the process eventually ends. The star cannot generate enough gravitational pressure to heat the core sufficiently to fuse carbon or oxygen into anything heavier. The nuclear reactions stop, the engine shuts down, and now something remarkable happens. The outer layers of the star, no longer held firmly in place by radiation pressure from the core, begin to drift away into space. They expand outward in a glowing shell of gas called a planetary nebula, one of the most visually stunning structures in all of astronomy. The name is a historical misnomer. Early astronomers peering through small telescopes thought these fuzzy, round objects looked like the disks of distant planets. They have nothing whatsoever to do with planets. They are the shed outer layers of dying stars, illuminated by the intense ultraviolet radiation of the exposed core at their center. If you could somehow watch this process unfold at accelerated speed, you would see something hauntingly beautiful. The dying star exhales its outer layers in successive pulses, each one sending a shell of gas expanding outward at speeds of tens of thousands of miles per hour. The gas carries with it elements forged in the star's interior, carbon and nitrogen and oxygen and trace amounts of heavier atoms, scattering them into the surrounding space. As the shells expand and thin, the blazingly hot core at the center is progressively revealed. The core's intense ultraviolet radiation ionizes the expanding gas, causing it to glow in vibrant colors. Oxygen atoms emit green and blue light, hydrogen glows red, nitrogen and sulfur contribute deeper reds and oranges. The result is an ethereal, luminous bubble expanding against the darkness of space. A dying star's final gift to the cosmos. Intricate, delicate, and temporary. Within a few tens of thousands of years, the nebula will have expanded and faded to invisibility. Its material dispersed into the interstellar medium, enriching it with heavier elements that will one day be incorporated into new stars, new planets, and perhaps new life. And what is left behind at the center, exposed after the outer layers have drifted away, is the core itself. A dense, blazingly hot compressed sphere of mostly carbon and oxygen, no longer generating any energy through fusion. No reactions are taking place. No fuel is being consumed. The nuclear furnace that powered the star for billions of years has gone permanently dark. This object is a white dwarf, and this is where the real story of the black dwarf begins. A white dwarf is one of the most extraordinary objects in the known universe, and understanding what it is, physically, is essential to understanding why a black dwarf cannot yet exist. A typical white dwarf contains roughly 1/2 to 8/10 the mass of the Sun, packed into a volume roughly the size of Earth. Think about that for a moment. Take a significant fraction of an entire star's mass, something that was once spread across a volume 1,000,000 times larger than Earth, and crush it down until it fits inside a sphere roughly 8,000 miles across. The density that results is almost beyond human comprehension. A single teaspoon of white dwarf material would weigh somewhere between 5 and 10 tons on the surface of Earth. A sugar cube-sized sample would weigh roughly as much as a large car. Imagine filling a standard drinking glass with white dwarf material. That glass would weigh roughly as much as a commercial airliner. A basketball-sized sphere of this material would weigh more than a fully loaded freight train. If you could somehow carve out a single cubic meter, a block about the size of a washing machine, it would weigh approximately 1 billion kilograms, 1 million tons, packed into a volume you could reach your arms around. There is no material on Earth that remotely approaches this. The densest natural element on our planet, osmium, has a density of about 22.5 grams per cubic centimeter. White dwarf material is roughly 50,000 to 100,000 times denser. Nothing in everyday experience comes close. The white dwarf matter is packed so tightly that the atoms themselves have been stripped of their structure. The electrons have been squeezed out of their normal orbits and now form a dense, degenerate gas filling the entire interior of the star. This leads to the most important question about a white dwarf. What holds it up? There is no fusion happening inside a white dwarf. No energy is being generated. So what prevents the relentless inward pull of gravity from crushing it further, from compressing it down to a neutron star or even a black hole? The answer comes not from astronomy, but from quantum mechanics. It is a phenomenon called electron degeneracy pressure, and it is one of the strangest and most counterintuitive forces in all of physics. At the incredible densities inside a white dwarf, the electrons are packed so unimaginably close together that a fundamental quantum mechanical law takes over. The Pauli exclusion principle states that no two electrons can occupy the same quantum state simultaneously. As the matter is compressed tighter and tighter, the electrons resist being squeezed into identical states. They push back, not with thermal energy, not because they are hot, but simply because the laws of quantum mechanics forbid them from being compressed any further without violating the exclusion principle. This resistance generates an outward pressure that is entirely independent of temperature. It does not come from heat. It does not come from radiation. It is a purely quantum mechanical effect. And here is the astonishing part. Even if you cooled the white dwarf all the way to absolute zero, this pressure would remain. It would still hold the star up. It is not the heat that supports a white dwarf. It is the quantum nature of electrons themselves. This is what makes a white dwarf fundamentally different from a normal star. A normal star would collapse if you removed its heat source. A white dwarf will not. It is stable regardless of its temperature, but there is a limit. This degeneracy pressure can only resist so much gravity. If more mass is added to a white dwarf, pushing it past a critical threshold, the electrons can no longer hold it up. That threshold is called the Chandrasekhar limit, named after the brilliant physicist who calculated it in 1930. At the age of just 19, while travelling by ship from India to England to begin his graduate studies at Cambridge, the limit is approximately 1.4 times the mass of the Sun. Any white dwarf below this mass is stable, held up indefinitely by electron degeneracy pressure. Any white dwarf that somehow exceeds this limit, perhaps by pulling matter from a companion star in a binary system, can collapse catastrophically, potentially triggering a Type 1a supernova, one of the most powerful explosions in the cosmos. But the vast majority of white dwarfs sit comfortably below this threshold. They will never collapse. They will never explode. They will simply sit there, held up by quantum mechanics, slowly and silently cooling for almost unimaginable stretches of time. And this is the critical point, the thing that defines a white dwarf's future and ultimately determines when the first black dwarf might form. A white dwarf is not generating energy. It has no fuel source. There is no fusion, no chemical burning, no gravitational contraction producing new heat. It is simply a hot object radiating its stored thermal energy into the cold vacuum of space. It glows because it is hot. The same way a metal poker pulled from a fire glows red, then orange, then fades to dull grey as it cools. But unlike a poker, which cools in minutes, a white dwarf cools over timescales that challenge even the cosmological imagination. When a white dwarf first forms, freshly exposed after its outer layers have drifted away as a planetary nebula, its surface temperature can exceed 100,000 degrees Kelvin. It is searingly hot, blazing with ultraviolet and even soft X-ray radiation. Over the first few 100 million years, the cooling is relatively rapid. The temperature drops noticeably. The white dwarf dims. It shifts from blue-white to yellow, its peak emission wavelength sliding down through the spectrum. But as it cools, something important changes. The rate of cooling slows down. Each subsequent drop in temperature takes longer than the one before. The physics governing this deceleration is fascinating and specific, and we will explore it in depth shortly. But the consequence is simple and profound. The colder a white dwarf gets, the harder it becomes for it to lose more heat. The process does not merely slow down, it decelerates continuously, stretching and stretching, asymptotically approaching but never quite reaching a final temperature of absolute zero. This is where the black dwarf enters the picture. A black dwarf is what you get when this cooling process finishes. When a white dwarf has radiated away every last bit of its stored thermal energy. When its surface temperature has dropped to match the temperature of the cosmic microwave background radiation. The faint afterglow of the Big Bang that permeates all of space, currently sitting at about 2.7 degrees above absolute zero. At that point, the white dwarf would reach thermal equilibrium with the universe around it. It would absorb exactly as much energy from the cosmic background as it emits. It would emit no detectable light, no infrared, no heat. It will be a sphere of crystallized carbon and oxygen, roughly the size of Earth, with roughly the mass of the Sun, drifting silently through the void. A stellar fossil in the most complete sense of the word. But the time required for a white dwarf to reach this state is not measured in billions of years. It is not even measured in trillions. Current models estimate that the cooling time for a typical white dwarf to reach what could reasonably be called a black dwarf state is somewhere between 10 to the 15th and 10 to the 25th years. Let me translate that. 10 to the 15th years is 1 quadrillion years. That is 1 million billion years. The universe right now is 13.8 billion years old. 1 quadrillion years is roughly 72,000 times longer than the entire current age of the universe. And that is the most optimistic estimate. Many models place the cooling time far longer, stretching to 10 to the 25th years or beyond, a number so immense that writing it out would require a 1 followed by 25 zeros. The oldest white dwarfs we have ever found have been cooling for nearly as long as the universe has existed. They reside in ancient globular clusters, dense spherical collections of stars that are among the oldest structures in the Milky Way. And after all that time, after billions of years of uninterrupted radiation into the void, they are still glowing, still warm, still visibly, detectably radiating heat. The cooling process that will eventually produce a black dwarf has, in even the most ancient stellar remnants we can find, barely started. The universe has not come close, not even within orders of magnitude of close. Think carefully about what this means. The oldest white dwarfs in the universe have been radiating heat for roughly 12 billion years, and they are still at thousands of degrees. The process requires at least a quadrillion years. The gap between where the coldest known white dwarfs are today and where they would need to be to qualify as black dwarfs is not a modest one. It is not a matter of waiting a few more billion years and checking back. The universe would need to age by a factor of approximately 100,000 before the first black dwarf could plausibly appear. We are, in the most literal and unambiguous sense, staggeringly early. This carries a profound implication that most people never stop to consider. We live in what astronomers call the stelliferous era, the age of stars. It is the period of cosmic history in which stars are being born, are actively shining, and are dying. To us, this era feels permanent. It is all humanity has ever known. Every civilization that has ever looked up at the night sky has seen stars burning. Every culture in human history has built stories and mythologies around those points of light. Every astronomer who has ever lived has studied objects that shine. Stars feel eternal and unchanging to us, but they are not. The stelliferous era is a temporary phase. It began when the first stars ignited, a few 100 million years after the Big Bang, and it will eventually end when the last stars burn out, perhaps 100 trillion years from now. And even that enormous span, the full duration of the age of stars from beginning to end, is a tiny fraction of the time required to produce a single black dwarf. From the perspective of the universe's total future, we are living in the opening moments. The first few pages of a story that will run for volumes upon volumes beyond our ability to count. Stars are still being born right now in molecular clouds and nebulae across the galaxy. New solar systems are forming. The cosmos is still bright, still warm, still churning with activity. The age of black dwarfs has not started. It is not close to starting. And the universe has an almost incomprehensible amount of aging to do before it arrives. So the black dwarf sits in an extraordinary position in our understanding of the cosmos. It is not speculative in the way that wormholes or faster than light travel are speculative. It does not require new or unproven physics. It is simply the inevitable end result of a cooling process that every physicist and every model agrees is happening right now, to every white dwarf in the universe, simultaneously. The physics is well understood, the outcome is certain, and yet the object itself does not exist, cannot exist, not today. Not for a stretch of time so immense that every event in the entire history of the universe, from the Big Bang to the formation of galaxies, to the first stirrings of life on Earth, to this very moment you are experiencing right now, would occupy less than the first heartbeat of the wait. That gap between inevitability and impossibility is what makes the black dwarf one of the most quietly fascinating objects in all of astrophysics. Not because of what it is, but because of what it tells us about time, about patience, and about how early we stand in the long, slow unfolding of the cosmos. To truly understand why this cooling demands so much time, why the timeline stretches from merely long to genuinely incomprehensible, we need to look much more closely at the physics happening inside a white dwarf. Because a white dwarf does not cool the way you might expect. The process is governed by strange, counterintuitive physics, and it is that physics that turns a simple act of losing heat into the longest wait in the history of everything. When you hold a hot cup of coffee, you already know what is going to happen. The heat dissipates. The coffee cools. Within an hour, maybe less, it reaches room temperature. The process is simple, intuitive, and universal. A hot object in a cooler environment loses heat until it matches its surroundings. This is one of the most fundamental observations in all of physics. Heat flows from hot to cold, always, without exception. A white dwarf follows the same basic principle. It is hot. The space around it is cold, so it radiates heat into the vacuum. Simple enough. But the details of how that cooling actually works are anything but simple, because a white dwarf is not a coffee cup. It is not a glowing ember. It is not a heated piece of metal left on a workshop bench to cool in the air. It is something profoundly and structurally different from any object you have ever held or touched. And the physics governing its interior makes its cooling process unlike anything else in the known universe. To understand why, you need to look beneath the surface, because a white dwarf is not a uniform ball of hot matter. It has layers, and those layers have radically different physical properties. And it is the relationship between these layers, how they store heat, how they transmit it, and how they resist letting it go, that transforms a straightforward process of heat loss into the longest cooling event in all of astrophysics. Picture the interior of a white dwarf as two distinct regions. At the center, making up the overwhelming majority of the star's mass, is the core. This core is composed almost entirely of carbon and oxygen, the products of the helium fusion that took place during the star's red giant phase. But this is not ordinary carbon and oxygen in any state you would recognize. The matter here is degenerate. The electrons have been stripped away from their parent atoms entirely, and now form a dense, freely moving sea of particles packed incredibly tightly together. The carbon and oxygen nuclei, bare ions without their electrons, sit embedded in this electron sea like stones resting on a beach. The density is staggering. We're talking about matter compressed to the point where every cubic centimeter weighs roughly 1,000,000 grams. The compression is beyond anything found naturally on Earth. This is not a gas. It is not a liquid. It is not a solid in any conventional sense. It is a state of matter that simply does not exist anywhere on Earth. a quantum mechanical configuration created solely by gravitational compression. Surrounding this degenerate core is an extremely thin envelope. This outer layer is made of hydrogen and helium, ordinary matter in a non-degenerate state, meaning the electrons still behave more or less normally. This envelope is astonishingly thin relative to the white dwarf's overall size. If the white dwarf were scaled to the size of an orange, the envelope would be thinner than the skin. It constitutes only a tiny fraction of the total mass, perhaps 1/10,000th or less. But this thin skin of ordinary matter plays a role in the cooling process that is vastly out of proportion to its size. It is the bottleneck, the gatekeeper, the insulating blanket that controls how quickly or how slowly the enormous reservoir of heat trapped in the core can leak out into space. Here is the key insight that explains why white dwarf cooling takes so impossibly long. The degenerate core is actually an excellent conductor of heat. The free electrons that fill it carry thermal energy with extraordinary efficiency, spreading it rapidly throughout the interior. The result is that the entire core stays at nearly the same temperature at any given time. Physicists call this isothermal. The center of the core, the midpoint, and the region just below the envelope are all essentially at the same temperature. There are no significant hotspots or cold spots. The heat is distributed almost perfectly evenly throughout the entire degenerate interior. But the heat cannot simply leap from the core into space. It has to pass through the envelope first. And the envelope is a terrible conductor. Unlike the degenerate core, where electrons flow freely and carry heat with ease, the envelope is opaque. It is made of ordinary matter, dense enough to block radiation, thick enough to trap heat. Photons generated in the core cannot stream freely outward through it. Instead, they are absorbed, re-emitted, absorbed again, bounced around, scattered, and redirected in a slow, tortuous, random walk toward the surface. This process is called radiative diffusion, and is agonizingly slow. The envelope acts like a thick insulating blanket wrapped around the core, trapping the heat inside and releasing it only in a thin, grudging trickle. The entire cooling rate of the white dwarf is controlled not by the enormous heat content of the core, but by how fast that heat can seep through this thin, stubbornly opaque layer of ordinary matter at the surface. Think of it this way. Imagine a massive underground reservoir of hot water, large enough to fill a lake, but the only exit is a single, narrow pipe, just a few inches across. The reservoir contains an immense amount of thermal energy, but the flow rate is governed entirely by the diameter of that pipe. The reservoir will take an extraordinarily long time to drain, not because it is running low on water, but because the exit is tiny. A white dwarf works on essentially the same principle. The core holds a tremendous amount of heat. The envelope lets it out through the thinnest of channels. The result is a cooling process that stretches across timescales that make geological ages look like the blink of an eye. Now, there is a law in physics that governs how much energy a hot object radiates from its surface. It is called the Stefan-Boltzmann law, and it states that the total energy radiated per unit area is proportional to the fourth power of the surface temperature. What this means in practice is that hotter objects radiate dramatically more energy than cooler ones. Double the temperature and the radiated energy increases by a factor of 16. Triple it, and the energy output increases 81-fold. The relationship is extremely steep. This has a crucial consequence for white dwarf cooling. When a white dwarf is young and hot, with a surface temperature of perhaps 100,000 degrees Kelvin, it is radiating an enormous amount of energy. Photons are streaming from its surface at a prodigious rate. The cooling at this stage is relatively fast, at least by white dwarf standards. The temperature drops noticeably over the first few 100 million years. The white dwarf dims visibly, shifting from brilliant blue-white toward a cooler, yellowish glow. But here is where the trap closes. As the surface cools, the Stefan Boltzmann law means the radiated energy drops sharply. A white dwarf at 50,000 degrees radiates 16 times less energy per unit area than one at 100,000 degrees. A white dwarf at 25,000 degrees radiates 16 times less than one at 50,000. At 10,000 degrees, the radiated energy is a mere 10,000th of what it was at 100,000 degrees. The cooler the white dwarf gets, the less energy it emits, and the slower it cools further. Each degree of cooling comes harder than the last. The process does not slow down linearly. It decelerates continuously, following a curve that flattens and stretches toward an endpoint it approaches, but never quite reaches. In 1952, a British astrophysicist named Leon Mestel published a landmark paper that laid out the first rigorous mathematical treatment of white dwarf cooling. Mestel showed that under certain simplifying assumptions, the luminosity of a white dwarf, the total energy it radiates per second, decreases as a power law over time. What this means is that the luminosity does not drop at a steady rate. Instead, it falls off following a curve that starts steep and gradually levels out. In the early stages, the white dwarf loses brightness quickly, but as time goes on, the rate of dimming decelerates. The intervals between equal steps of luminosity decrease, grow longer and longer. Mestel's cooling theory, refined and built upon by generations of astrophysicists since, remains the foundation of our understanding of white dwarf evolution. The details have been updated. Better models of the envelope's opacity, more accurate equations of state for the degenerate core, improved nuclear physics. But the essential picture Mestel painted has held up beautifully for over 70 years. A white dwarf is a hot degenerate core, wrapped in an insulating blanket, slowly bleeding its heat into space at a rate that diminishes over time. The cooling follows a well-understood mathematical trajectory, and that trajectory, plotted out across the full span of time it requires, stretches to truly staggering lengths. But the cooling curve has another feature that makes the wait even longer than you might expect, and it involves one of the most extraordinary phase transitions in all of stellar physics: crystallization. As a white dwarf cools, its internal temperature gradually decreases. Remember, the degenerate core is nearly isothermal, so the entire core cools more or less uniformly. For the first few billion years, the carbon and oxygen ions in the core are in a liquid-like state. They are positively charged ions embedded in a sea of degenerate electrons, jostling and moving freely, interacting through Coulomb forces, the electrostatic repulsion between like charges. But as the temperature drops, the thermal energy of these ions decreases. They move less and less vigorously, and at some critical temperature, typically when the core has cooled to somewhere in the vicinity of a few million degrees Kelvin internally, something remarkable happens. The ions stop moving freely and begin to lock into fixed positions relative to one another. They settle into a regular, repeating geometric pattern, a crystal lattice. The core of the white dwarf is solidifying. This is crystallization, and it is happening right now in old white dwarfs across the galaxy. The core of a sufficiently old white dwarf is not a liquid. It is not a gas. It is a crystal. A massive, ultra-dense crystal made of carbon and oxygen ions arranged in what physicists believe is a body-centered cubic lattice, one of the most common crystal structures in nature. Some popular descriptions compare this to a diamond, and while the comparison is imperfect because the conditions and bonding mechanisms are very different from terrestrial diamond, the evocative image captures something true. The core of an old white dwarf is a crystalline structure, rigid and ordered, with ions locked in precise geometric positions, surrounded by a sea of free electrons. A cosmic gemstone roughly the size of Earth. But the most important thing about crystallization for our story is not what the crystal looks like. It is what the crystallization process does to the cooling timeline. Because when the core crystallizes, it releases energy. This is latent heat, the energy released during a phase transition, the same phenomenon that causes water to release heat when it freezes into ice. As the carbon and oxygen ions settle into their crystalline positions, they give up thermal energy. But there is an additional and even more significant energy source. When the core crystallizes, the heavier oxygen nuclei tend to sink toward the center, while the lighter carbon nuclei float upward. This gravitational settling releases gravitational potential energy, which is converted into heat. The effect is substantial. This additional heat source acts like a second wind, injecting energy back into the white dwarf just as it is trying to cool, slowing the temperature decline and extending the cooling time even further. Think of it as trying to drain a bathtub while someone else is slowly pouring water back in. You are still making progress. The water level is still dropping. But the rate of drainage has decreased because you are fighting a secondary input. Crystallization does essentially the same thing. It adds an internal heat source to a white dwarf that has no other energy source, temporarily propping up its luminosity and delaying the long descent toward darkness. The crystallization phase does not last forever. Eventually the latent heat is fully released, the gravitational settling is complete, and the core finishes solidifying. But by the time this process concludes, it has added billions of additional years to the cooling timeline. Models suggest that crystallization can slow the cooling of a white dwarf by roughly 15 to 25% of its total cooling age, depending on the mass and composition. For a white dwarf that might otherwise take a certain immense span to cool to near zero, crystallization adds a significant additional stretch on top. For decades, this crystallization process was purely theoretical. The models predicted it with confidence, but nobody had seen it happen. The interiors of white dwarfs are inaccessible to direct observation. You cannot crack one open and look at the crystal forming inside. But in 2019, a team of astronomers found the evidence in a place no one had been able to look before, at least not with sufficient precision. They used data from the European Space Agency's Gaia spacecraft, which was conducting the most detailed survey of stellar positions and brightnesses ever attempted, cataloguing over 1 billion stars in the Milky Way with extraordinary accuracy. By plotting thousands of white dwarfs on a diagram comparing their brightness to their color, the team discovered something striking. There was a pileup. An excess of white dwarfs clustered at a specific brightness and color range. exactly the range where crystallization models predicted the cooling should temporarily stall. The theory said that when crystallization begins, the release of latent heat and gravitational energy should cause white dwarfs to linger at a particular luminosity for longer than they otherwise would, spending extra time at that stage before continuing to fade. This lingering should produce a visible excess in the population, more white dwarfs at that brightness than the smooth cooling curve alone would predict. And that is exactly what the data showed. The pileup was there, right where the models said it should be. It was the first direct observational evidence that white dwarf cores crystallize, and it confirmed that the theoretical cooling models, the same models that predict the impossibly long timescales leading to a black dwarf, are not merely plausible, they are correct. After crystallization is complete, the cooling enters yet another distinct regime. The crystallized core now follows different thermal physics than it did in its liquid state. In particular, the heat capacity of the solid lattice drops, with temperature following a relationship first described by the physicist Peter Debye in the early 20th century. The Debye model of solid-state physics tells us that at low temperatures, the heat capacity of a crystalline solid decreases as the cube of the temperature. This means that as the white dwarf continues to cool, the core's ability to store heat diminishes. There is less thermal energy available to radiate. But the surface luminosity is also decreasing, because the Stefan Boltzmann law ties radiated energy to the fourth power of the surface temperature. These two effects interact in a complex dance, and the net result is that the cooling continues to decelerate. Each subsequent drop in temperature requires a proportionally longer wait. The cooling curve of a white dwarf, plotted on a graph of luminosity versus time, looks like a slope that starts moderately steep and then gradually flattens out, approaching but never quite reaching the horizontal. In the first 100 million years, the luminosity drops significantly. Over the next 1 billion years, it drops further, but more slowly. Over 10 billion years, it drops further still, but the rate of change is now almost imperceptible on the graph. And the curve keeps going, stretching outward through hundreds of billions, then trillions, then tens of trillions of years. The luminosity creeping downward in ever smaller increments, each step taking longer than the last. The white dwarf dimming so gradually that from any practical measurement standpoint, it barely seems to be changing at all. Let me put some concrete numbers on this to show just how absurd the timescales become. A freshly formed white dwarf, perhaps 1 billion years old, might have a surface temperature in the range of 20,000 degrees Kelvin. It would still glow a brilliant blue-white, easily visible through a telescope. At around 3 billion years, the surface has cooled to perhaps 10,000 degrees, still visibly white-hot. The white dwarf is dim by stellar standards, but is unmistakably radiating. By about 8 billion years, perhaps 5,000 to 6,000 degrees, it glows with a warm yellowish light, similar in color temperature to the sun, though vastly dimmer. At 12 billion years, roughly the age of the oldest known white dwarfs in the universe right now, the surface sits at perhaps 3,000 to 4,000 degrees. It is glowing a faint, dull red, barely visible, but still warm, still detectably radiating. Now here is where the numbers leave the realm of the familiar entirely. To cool from 4,000 degrees down to 1,000 degrees requires not another 12 billion years, but roughly 100 billion years. That is more than 7 times the current age of the universe. To continue cooling from 1,000 degrees to a few hundred degrees, models suggest this requires trillions of years. And the final approach, crawling from a few hundred degrees down to the background temperature of the cosmos, roughly 2.7 degrees Kelvin, is the slowest stretch of all. This final phase alone could require timescales on the order of 1,000,000 trillion years or more. And even that number is deceptive, because the background temperature of the universe is not fixed. As the universe continues to expand, the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space, is itself cooling. It is getting colder as space stretches, and the wavelengths of those ancient photons lengthen. By the time a white dwarf has cooled to a few degrees above absolute zero, the background temperature of the universe may have dropped to a fraction of a degree. The goalpost is moving. The target temperature the white dwarf needs to reach to be in thermal equilibrium with its surroundings is falling as the universe ages and expands. This means the cooling process is chasing a receding target, which extends the timeline even further. The cooling of a white dwarf is not merely slow, it is designed by the fundamental physics governing it to decelerate at every stage. The insulating envelope restricts the heat flow. The Stefan Boltzmann law ensures that cooler surfaces radiate less. Crystallization injects additional heat just when the white dwarf is trying to lose it. The Debye model reduces the heat capacity at low temperatures, meaning there is less energy to lose, but the loss rate has also plummeted. And the expanding universe keeps lowering the background temperature, stretching the approach to equilibrium. Every single factor in the equation conspires to make the process longer. When you compile all of these effects together and run the models forward, the total time required for a white dwarf to cool completely, to reach a state that could genuinely be called a black dwarf, comes out to somewhere between 10 to the 15 and 10 to the 25 years. The lower end, 10 to the 15th power, is 1 quadrillion years, 1,000,000 billion years. To put that in perspective, the universe would need to live out its entire current lifespan tens of thousands of times over before even the fastest cooling white dwarf could finish. And that is the floor estimate. Many models, particularly those accounting for the most massive white dwarfs with larger heat reservoirs and the ongoing expansion of the universe, push the cooling time toward 10 to the 25th years, 10 septillion years. To write that number out, you would need a 1 followed by 25 zeros. Let me try to make these numbers feel real, because they resist comprehension. Imagine the entire history of the universe from the Big Bang to this exact moment as a single second. One tick of a clock. At that scale, the time required for a white dwarf to cool to a black dwarf at the most optimistic estimate would be roughly 20 hours. A full day of cooling for 1 second of cosmic history. And the pessimistic estimate would stretch to roughly 23 million years. The entire history of the cosmos compressed into 1 second. And the cooling time stretches to millions of years at the same scale. That is the gulf we're talking about. Or consider it differently. The universe has existed for about 13.8 billion years. In that time, galaxies formed, billions of generations of stars lived and died, heavy elements were synthesized in supernova furnaces, planets coalesced from cosmic debris, life arose on at least one world, and conscious beings evolved to the point where they could contemplate their own existence. all of that fits within the first 13.8 billion years. The first black dwarf would not appear for at least another 999 trillion, 986 billion years at the very minimum. Everything that has ever happened, all of cosmic history, fits into less than 1/100% of the time needed for the first black dwarf to form. We are not just early, we are unimaginably, absurdly early. We exist in a cosmos so young that the dominant feature of its deep future, cold dead stars drifting in total darkness, has not produced a single example yet. The white dwarf cools. It will always cool. The physics is inevitable, but the pace of that cooling is governed by every layer of its structure, every quantum mechanical property of its interior, every thermodynamic law that dictates how energy flows from hot to cold. And every one of those factors works together to stretch the cooling time past the limits of human comprehension. The result is an object that the universe is guaranteed to produce, but that exists nowhere, and will exist nowhere for a span of time that makes the current age of the cosmos look like the first breath of a life that will last for ages beyond counting. So now you understand the physics. You understand why a white dwarf cools the way it does. You understand the insulating envelope, the degenerate core, the crystallization that adds heat back just when the star is trying to lose it, and the mathematical curve that flattens and stretches toward a destination it will not reach for an almost incomprehensible span of time. The mechanism is clear. The outcome is certain. A black dwarf must eventually form. But certainty about the future is not the same as existence in the present. And to appreciate just how far the universe is from producing its first black dwarf, we need to take a hard, unflinching look at the numbers. We need to hold the age of the universe in one hand and the cooling timescale in the other and actually compare them. Because when you do, the gap that opens up is not merely large, it is so staggeringly vast that it forces you to rethink what the word young means when applied to the entire cosmos. The universe is approximately 13.8 billion years old. We know this with remarkable precision, not from a single measurement, but from multiple independent lines of evidence that all converge on the same answer. The cosmic microwave background, the faint afterglow of radiation left over from when the universe was only 380,000 years old, carries within its temperature fluctuations a detailed imprint of the early cosmos. By analyzing the pattern of these fluctuations, the size and spacing of the hot and cold spots, cosmologists can extract fundamental properties of the universe, including its age. Missions like the Wilkinson Microwave Anisotropy Probe, known as WMAP, and the European Space Agency's Planck satellite have measured this background radiation with extraordinary precision, giving us an age of 13.799 billion years with an uncertainty of only about 20 million years. That is a measurement accurate to better than 1%. We know how old the universe is with remarkable confidence. Independent confirmation comes from completely different methods. The expansion rate of the universe gives a consistent answer. The ages of the oldest known stars all fall below 13.8 billion years, exactly as they should if nothing can be older than the universe itself. The abundances of light elements forged in the first few minutes after the Big Bang during a process called Big Bang nucleosynthesis match predictions based on a universe of this age. Every line of evidence points to the same conclusion. The cosmos has existed for roughly 13.8 billion years. Not a rough estimate, not a guess. A well-constrained, multiply confirmed measurement, 13.8 billion years. It sounds like an enormous number, and from a human perspective, it is. Civilizations have risen and fallen in the space of centuries. The entire recorded history of our species spans only about 5,000 years. Modern humans have existed for roughly 300,000 years. Life on Earth emerged about 3.8 billion years ago. The Earth itself formed about 4.54 billion years ago. The universe predates all of this by a wide margin. It has existed for roughly 3 times longer than the Earth has been around, 3 times longer than the planet beneath your feet has existed. By any human measure, 13.8 billion years is an eternity, but it is not an eternity. That is the critical point. It is a specific, finite, measurable span of time. And when you compare it to the timescale required to cool a white dwarf into a black dwarf, it shrinks from seeming eternal to seeming astonishingly brief. The most conservative models, the ones that assume the most favorable conditions for rapid cooling, estimate that the minimum time required for a typical white dwarf to reach thermal equilibrium with the surrounding cosmos is on the order of 10 to the 15th years. 1 quadrillion years. Let me place these two numbers side by side so the comparison is absolutely clear. The universe has existed for approximately 13.8 times 10 to the 9th years. The minimum cooling time is approximately 10 to the 15th years. That means the cooling time is roughly 72,000 times longer than the entire current age of the universe. If you represented the age of the universe as a single step, the cooling time would be a journey of 72,000 steps. We have taken one step. The journey has barely begun. And that is the optimistic scenario. More detailed models that account for the full range of white dwarf masses, compositions, envelope thicknesses, and the ongoing expansion and cooling of the universe push the required timescale to 10 to the 20th years or beyond. At 10 to the 20th years, the cooling time is not 72,000 times the age of the universe. It is 7 billion times the age of the universe. The gap is no longer a chasm. It is an abyss so deep that the concept of depth itself starts to lose meaning. Let me try to make this proportion tangible, because raw numbers at this scale slide off the mind without leaving a mark. Imagine the entire cooling time of a white dwarf, from freshly formed stellar corpse to cold, dark black dwarf, represented as a single calendar year. January 1st is the moment the white dwarf forms. December 31st at midnight is the moment it finally reaches thermal equilibrium and becomes a black dwarf. Every day in this calendar represents roughly 2.7 trillion years. Every hour represents roughly 113 billion years. Every minute represents roughly 1.9 billion years. Now ask yourself, where in this calendar year does the present moment fall? The universe is 13.8 billion years old. The oldest white dwarfs have been cooling for roughly 12 billion years. 12 billion years, mapped onto a calendar that spans a quadrillion years, puts us at approximately 6 minutes and 20 seconds past midnight on January 1st. Not January 2nd, not the morning of January 1st, the first 7 minutes. The ball has just dropped. The confetti is still in the air. And the white dwarf has 364 days, 23 hours, and 53 minutes of cooling left to go. That is where we are. That is how young the universe is relative to the timescale of black dwarf formation. We exist in the first fraction of a percent of the weight. so close to the beginning that we are barely distinguishable from the starting moment itself. We are not waiting for a pot to boil. We are not waiting for a glacier to carve a valley. We are not even waiting for a continent to drift across an ocean. We are waiting for a process so slow that the entire geological, biological, and cosmological history of the universe to date does not register as a meaningful fraction of the total weight. Everything that has ever happened, the formation of the first stars, the birth of galaxies, the emergence of life, the evolution of intelligence, all of it fits inside the first 1/72,000th of the cooling time. It is the opening sentence of a book that will run for volumes beyond counting. Now, you might wonder whether we have actually looked, whether astronomers have searched the sky for white dwarfs that might have cooled significantly, that might be approaching the black dwarf state, even if they have not reached it yet. The answer is yes, they have looked, and what they have found confirms the theoretical picture with uncomfortable precision. But finding the oldest, coldest white dwarfs is extraordinarily difficult. These objects are among the faintest things in the entire sky. A white dwarf that has been cooling for 12 billion years has a luminosity roughly 1/10,000th that of the Sun. It emits most of its remaining energy in the infrared rather than visible light. To detect such objects requires deep imaging surveys, long exposures with the most sensitive cameras mounted on the largest telescopes, collecting photons one by one from objects that barely register above the background noise of the sky itself. It is the astronomical equivalent of trying to spot a single dying ember in a dark field from miles away. And there is a further complication. A very faint, very cool white dwarf looks almost identical to a very distant background galaxy in a standard photograph. Both appear as a barely perceptible smudge of light. To distinguish between them, astronomers rely on a technique called proper motion detection. Stars in our galaxy, including white dwarfs, are relatively close to us and move perceptibly across the sky over years or decades. Distant galaxies do not. By comparing images taken years apart, astronomers can identify objects that have shifted position, confirming they are nearby stars rather than distant galaxies billions of light years away. This is painstaking work. It requires comparing millions of objects across multiple epochs of observation, looking for tiny shifts in position that reveal a faint object's true nature. Many of the coolest known white dwarfs were discovered precisely this way, picked out of the background by their almost imperceptible drift across the sky over decades of patient observation. Even after finding these objects, measuring their temperatures is a challenge. The spectral energy distribution of an extremely cool white dwarf, the way its feeble light is distributed across different wavelengths, must be compared against theoretical atmosphere models to extract a temperature estimate. At very low temperatures, the physics of the white dwarf's thin atmospheric layer becomes complicated. Molecular hydrogen can form, altering the opacity in ways that make the models more uncertain. The error bars on the temperatures of the very coolest known white dwarfs can be several hundred degrees, a significant fraction of the measurement itself. Despite all of this, the conclusions are robust. The coldest white dwarfs we can find, even pushing our instruments to their absolute limits, are still at thousands of degrees. The oldest known white dwarfs in the universe are found in globular clusters. These are ancient, tightly packed, spherical collections of stars, containing anywhere from a few 100,000 to over 1 million stars bound together by their mutual gravity. Globular clusters are among the most ancient structures in the Milky Way. They formed very early in the galaxy's history, some as far back as 12 to 13 billion years ago, when the universe itself was less than 1 billion years old. The stars in these clusters are overwhelmingly old. Most of the original massive, hot, bright stars burned through their fuel and died billions of years ago. What remains are low-mass main-sequence stars, still burning slowly, and the remnants of intermediate mass stars that died long ago and left behind white dwarfs. These white dwarfs in globular clusters are among the oldest stellar remnants we can observe. Some have been cooling for 11 to 12 billion years, nearly the entire age of the universe. They have been radiating their residual heat into the void since before the Earth formed, since before the Sun ignited, since the Milky Way was still assembling itself from smaller galactic fragments. And after all that time, what are their temperatures? They sit at roughly 3,000 to 4,000 degrees Kelvin. They're still glowing. Faintly, yes. At the very dim red end of the visible spectrum, barely perceptible even to powerful telescopes. But they're still warm, still detectably radiating, still visibly, unambiguously alive in the thermal sense. Consider one specific example. The globular cluster NGC6397 is one of the closest globular clusters to Earth, located about 7,800 light-years away. It is also one of the oldest, with an estimated age of roughly 13 billion years. Observations with the Hubble Space Telescope have identified the faintest, coolest white dwarfs in this cluster. These are stars that have been dead and cooling for nearly as long as the universe has existed. Their surface temperatures are in the range of 3,500 to 4,000 degrees Kelvin. They are dim. They are fading. But they are nowhere close to the endpoint. They are not even within shouting distance of becoming black dwarfs. After nearly 13 billion years of uninterrupted cooling, they remain thousands of degrees above the cosmic background temperature. The cooling process, for all its relentless inevitability, has accomplished only the very first fraction of the work it will eventually complete. The globular cluster Messier 4 tells a similar story. Located about 7,200 light-years from Earth, Messier 4 contains white dwarfs that have been observed in extraordinary detail. The faintest ones are approaching the limits of what our telescopes can detect, glowing at temperatures of a few thousand degrees. Some of the coolest white dwarfs found anywhere are in these ancient clusters, and every single one of them is still radiating, still warm, still thousands of degrees above the temperature that would qualify them as black dwarfs. There are also isolated white dwarfs in the field population of the Milky Way that rank among the coldest known. One example often cited in the literature is a white dwarf catalogued as WD0346 plus 246. This object has an estimated surface temperature of roughly 3,000 degrees Kelvin and an estimated cooling age of around 11 billion years. It is extraordinarily dim, so faint that detecting it required dedicated deep imaging campaigns, and yet it is still radiating, still warm, still an active emitter of photons, however few and however feeble. It is among the very coldest white dwarfs ever measured, and it is not even close to being a black dwarf. One of the most powerful tools astronomers have for studying white dwarf cooling at the population level is something called the white dwarf luminosity function. Rather than examining individual objects, the luminosity function counts how many white dwarfs exist at each level of brightness across a given population. You survey a region of the sky, identify every white dwarf you can find, measure each one's luminosity, and then plot the number of white dwarfs in each luminosity bin. The result is a distribution that reveals something remarkable about the age of the population. At high luminosities, where the white dwarfs are young and hot, the numbers build steadily. There are relatively few very bright white dwarfs because they cool quickly through this phase and move to lower luminosities. As you move to fainter and fainter luminosities, the numbers increase because white dwarfs accumulate at lower brightness levels. They spend more time at each successively dimmer stage because the cooling decelerates. The luminosity function rises as you move toward fainter objects. But then, at a certain critical faintness, the distribution does not gradually taper off. It drops sharply. There is a cutoff, an edge, a cliff in the data where the population of white dwarfs simply stops. Below a certain luminosity, there are essentially no white dwarfs at all. This cutoff is not an observational limitation. It is not that our telescopes cannot see fainter objects, although that is also true. The cutoff is real. It represents the faintest luminosity that a white dwarf can reach given the finite age of the population. No white dwarf has had time to cool below this threshold because the universe, or the particular stellar population being studied, simply is not old enough. The cutoff is the age of the population stamped directly into the data. It is the universe's youth made visible, converted from an abstract number into a sharp edge in an observed distribution. When astronomers measure this cutoff in the disk of the Milky Way, they find it corresponds to a cooling age of roughly 8 to 10 billion years, consistent with the age of the galactic disk. When they measure it in globular clusters, the cutoff corresponds to cooling ages of 11 to 12 billion years, consistent with these clusters forming in the first billion years of cosmic history. And in every case, the cutoff falls at luminosities and temperatures far, far above what would be needed for a black dwarf. The cliff edge in the data is not even remotely close to the bottom of the theoretical cooling curve. The luminosity function is telling us, in the clearest possible terms, that the cooling process has barely started. This is the observational reality. Every white dwarf ever observed, without exception, is still radiating thermal energy. The coldest ones have surface temperatures in the low thousands of degrees. None has been found below about 3,000 degrees Kelvin. The theoretical prediction says the cooling to black dwarf status requires at least a quadrillion years. The observational data confirms that after 12 or 13 billion years, the coolest white dwarfs are still at thousands of degrees. The data and the theory are in perfect agreement. The universe is simply too young. What this tells us about the black dwarf as a physical object is worth stating plainly, because it is a genuinely unusual situation in astrophysics. The black dwarf has never been observed. It cannot be observed. This is not a limitation of our instruments. It is not a challenge that a better telescope will solve. The James Webb Space Telescope, the most powerful space observatory ever built, cannot find a black dwarf. A telescope 1,000 times more powerful could not find one. A hypothetical detector that could survey every object in the observable universe, every star, every planet, every moon, every grain of dust in every galaxy, would not find a single black dwarf, because none exist. The objects have not formed yet. They are not hiding. They are not too faint. They simply do not exist anywhere in the cosmos at this moment. They exist only in equations, in models, in the mathematics of thermodynamics and quantum mechanics and stellar evolution. They are predictions, not observations. Theoretical necessities, not empirical realities. This makes the black dwarf something quite rare in modern astrophysics. Most of the objects we discuss, even the exotic ones, have some observational basis. Neutron stars were predicted theoretically before they were discovered, but they were eventually discovered. Black holes were theoretical for decades before observational evidence confirmed their existence. Gravitational waves were predicted by Einstein in 1916 and finally detected a century later. Dark matter and dark energy are inferred from observations, even though we do not know what they are. But the black dwarf occupies a category almost entirely its own. It is a prediction that cannot be confirmed by observation because the universe has not existed long enough to produce the thing being predicted. The prediction is not in doubt. No serious astrophysicist questions whether black dwarfs will eventually form. The physics is too well understood, too well tested, too internally consistent for the conclusion to be wrong. But confirmation through observation is not just difficult. It is physically impossible at this stage of cosmic history. There is something quietly profound about this. It tells us something about where we stand in the timeline of the universe. Not where we stand geographically, not where we are in space, but where we are in time. We live in the stelliferous era, the age of stars. This era began roughly a few 100 million years after the Big Bang, when the first stars ignited from collapsing clouds of hydrogen and helium. It continues today, and will continue for a very long time by human standards, perhaps another 100 trillion years. During this era, galaxies churn with activity, new stars are born in dense molecular clouds, old stars die, scattering heavy elements into the interstellar medium that are then recycled into the next generation. Planets form. On at least one planet, life arose and evolved into beings capable of looking upward and asking questions about what they saw. This era feels permanent to us. It is all we have ever known. Every human civilization has existed within this stelliferous era. Every astronomer who has ever looked through a telescope has seen a sky full of burning stars. The idea of a universe without stars is alien to us. It seems wrong somehow, empty, lifeless. But the stelliferous era is not permanent. It is a phase, a chapter. And from the perspective of the universe's total expected lifespan, it is a very brief chapter. If you imagine the total future of the universe stretched out like a timeline, the stelliferous era occupies only the very beginning. Stars will continue forming for another 100 trillion years or so. But the rate of star formation is already declining. The raw material, the hydrogen gas from which new stars condense, is being used up. Galaxies are growing quieter. The great era of cosmic fireworks, when supernova explosions lit up the sky and new star systems were born in glowing nebulae, is already past its peak. We live in the autumn of star formation, not the spring. The universe still glows, but the light is fading. And yet, within this narrow window of cosmic youth, the cooling white dwarfs have already proven themselves to be extraordinarily useful scientific tools. Because even though they will not become black dwarfs for ages beyond reckoning, their cooling rates are well enough understood that astronomers use them as clocks. Precise, reliable, cosmological clocks. The field is called white dwarf cosmochronology, and it exploits the one thing that makes white dwarf cooling simultaneously frustrating and useful. The cooling rate is predictable, Given a white dwarf's mass, composition, and atmospheric type, the physics of its cooling curve is well constrained by theory. A hotter white dwarf is younger. A cooler one is older. By measuring the surface temperature or luminosity of a white dwarf and comparing it to the theoretical cooling models, astronomers can determine how long ago that white dwarf formed, which in turn tells them when the progenitor star died. This technique has been applied to some of the most fundamental questions in galactic astronomy. How old is the disk of the Milky Way? When did the first stars in our galaxy form? How does the age of the galactic disk compare to the age of the galactic halo, the diffuse spherical region of old stars surrounding the flattened disk? Answering these questions requires finding the oldest white dwarfs in each population and measuring their temperatures. The oldest white dwarfs are the faintest and the coolest, and finding them requires extraordinarily deep imaging surveys that can detect objects far dimmer than ordinary stars. But when astronomers succeed, the results are powerful. By identifying the faintest white dwarfs in the Milky Way's disk, astronomers have established that the disk is roughly 8 to 10 billion years old. This tells us when the Milky Way's thin disk, the flattened structure in which the Sun resides, settled into its current form and began forming stars in an organized rotating plane. The halo white dwarfs tell a different story. Found in globular clusters and in the sparse, spherical distribution of old stars surrounding the disk, the coolest halo white dwarfs are dimmer and older. Their cooling ages indicate the halo is roughly 11 to 13 billion years old, consistent with the halo forming early in the Milky Way's history, before the disk had fully assembled. This age layering, an older halo surrounding a younger disk, matches the hierarchical model of galaxy formation, where large galaxies build up over time through mergers of smaller systems. White dwarf cosmochronology also provides an independent check on the age of the universe itself. The oldest white dwarfs in the most ancient globular clusters set a firm lower bound. The universe must be at least as old as the oldest objects in it. When the cooling ages of the oldest known white dwarfs come out to roughly 11 to 12 billion years, and you add the main sequence lifetime of their progenitor stars, typically another 1 to 2 billion years, you get total ages of 12 to 13 billion years for these stellar populations. This is entirely consistent with the independently measured age of 13.8 billion years from the cosmic microwave background. The agreement between these completely different methods, one based on microwave radiation from the early universe, and the other based on the faintly glowing embers of dead stars, is a powerful confirmation that our understanding of both cosmology and stellar physics is on the right track. There is something beautifully circular about this. The very process that prevents black dwarfs from existing, the slow, relentless, predictable cooling of white dwarfs, is the same process that allows us to measure the ages of stellar populations and constrain the history of our galaxy. The frustration of the white dwarf's glacial cooling is also its scientific gift. Because the cooling is so slow and so predictable, each white dwarf carries its age written in its temperature. The dimmer it is, the longer it has been dead. And by reading that temperature, by placing it on the theoretical cooling curve, astronomers can reconstruct the history of stellar death in a given population, and from there, the history of stellar birth, and from there, the formation history of the galaxy itself. The coldest white dwarfs, the ones hovering at 3,000 to 4,000 degrees after billions of years of cooling, are, in a sense, the most valuable. They are the most informative because they set the strongest constraints. They tell us the age of the oldest stellar populations. They define the floor below which no white dwarf has had time to cool. They draw a line in the sand and say, this is how old the oldest things in the universe are, and no older, because the universe itself has only existed for this long. Every white dwarf cooler than a certain threshold would require more time to reach that temperature than the universe has provided. If we found one too cold, too dim, too far along its cooling curve, it would create a crisis. It would mean either our cooling models are wrong or our age for the universe is wrong. The fact that no such crisis has occurred, the fact that the coolest observed white dwarfs are perfectly consistent with cooling ages slightly less than the age of the universe, is a quiet but powerful validation of our entire framework of stellar and cosmological physics. So the white dwarf sits at an intersection of frustration and utility. It is frustrating because its cooling is so slow that the theoretical endpoint, the black dwarf, remains forever out of observational reach. But it is useful precisely because that slowness is predictable, calculable, and informative. The white dwarf is a clock that will run for ages beyond our ability to witness. But right now, in this early, bright, star-filled era of cosmic history, the time it has already recorded is enough to tell us when the stars began to die, how old our galaxy's structures are, and how young the universe truly is. And it is young. That is the message the white dwarfs are delivering, quietly from their dim positions in the fading corners of ancient star clusters. The universe is young, not young in the way a child is young, with the majority of life still ahead. Young in the way a newborn is young, eyes barely open, the overwhelming majority of existence stretching ahead in a future so vast and so different from the present that imagining it requires abandoning almost every assumption about what the cosmos looks like. The stars will not always shine, the galaxies will not always glow, the night sky will not always be full of light. All of this, the burning and the shining and the warmth, is temporary, a phase, a moment. The universe in its current form is a brief, bright flash in what will be an immeasurably long darkness. And the black dwarf, cold and dark and patient, belongs to that darkness. It is waiting, not as an object that exists and bides its time, but as a certainty that has not yet been born, an inevitability that the universe will spend ages beyond counting slowly, quietly assembling from the fading embers of its once bright stars. So let us go there. Let us leave the present behind entirely and travel forward in time, past every boundary of human experience, past every era that has a name, past every epoch that could possibly contain anything resembling the cosmos we know. Let us travel to the age of the black dwarf, because while no black dwarf exists today, the laws of physics are patient. They do not forget, and they guarantee, with the quiet certainty of thermodynamics, that the black dwarf will eventually arrive. The question is what the universe will look like when it does. The first thing that has to happen is the end of star formation. Right now, across the Milky Way and in galaxies throughout the observable universe, new stars are being born. Dense clouds of molecular hydrogen collapse under their own gravity, fragment, heat up, and ignite nuclear fusion. Each new star represents a fresh injection of light and heat into the cosmos. But this process is not sustainable. It depends on a raw material, hydrogen gas, that is finite. Every star that forms consumes a portion of the available supply. Some of that hydrogen is locked permanently inside stellar remnants, white dwarfs, neutron stars, black holes, objects that will never return their material to the interstellar medium. Some is expelled back into space through stellar winds and supernova explosions, but even that recycled gas gradually becomes enriched with heavier elements that change the dynamics of subsequent star formation. The rate of star formation across the universe has been declining for billions of years. It peaked roughly 10 to 11 billion years ago, and has been dropping steadily since. We live in an era of diminishing returns, where each generation of new stars is smaller and less vigorous than the one before. The last stars to form will be the smallest ones, red dwarfs. These are stars with masses as low as roughly 8% the mass of the Sun, barely large enough to sustain hydrogen fusion in their cores. They are dim, cool, and extraordinarily efficient. While a star like the Sun burns through its hydrogen in about 10 billion years, a small red dwarf can stretch its fuel supply across trillions of years. A red dwarf with a tenth the mass of the Sun could theoretically burn for 10 trillion years or more, nearly 1,000 times the current age of the universe. These tiny, frugal stars will be the last lights still shining in the cosmos, but even they will eventually run out. Sometime around 100 trillion years from now, give or take, the last red dwarf in the universe will exhaust its hydrogen fuel. Its core will contract. Its outer layers may briefly swell before being shed. And at its center, a new white dwarf will be born. The very last white dwarf the universe will ever produce. And then the lights will go out. Not suddenly, not dramatically. The final red dwarf will not explode. It will simply fade, dim past visibility, cool below the threshold of detectability, and the stelliferous era, the age of stars, the only age of the universe that has ever contained light generated by nuclear fusion, will be over, permanently, irreversibly. The cosmos will never produce another star. What remains is a universe of leftovers. Astronomers Fred Adams and Greg Laughlin, who mapped out the long-term future of the cosmos in meticulous detail, called this the degenerate era. It is a cosmos populated entirely by stellar corpses, white dwarfs, slowly cooling, emitting less and less radiation with each passing age. Neutron stars, gradually losing the rotational energy that powers their magnetic fields and radio pulses, winding down like cosmic clocks running out of spring. Black holes, sitting in the darkness, growing only if something happens to fall into them, otherwise simply existing. No new energy is being generated anywhere. The universe runs on residual heat, the thermal afterglow of an era that ended ages ago. But the degenerate era is not simply the stelliferous era with the lights turned off. The structure of the cosmos itself will change profoundly. Galaxies, those vast collections of billions of stars held together by gravity, will slowly dissolve. Over timescales of quintillions and tens of quintillions of years, gravitational interactions between stellar remnants will gradually eject objects from their parent galaxies. Each close encounter between two orbiting remnants is a gravitational negotiation. Sometimes one object gains energy at the expense of the other. Over uncountable repetitions of this process, some objects are flung outward, escaping the galaxy's gravitational pull entirely, and drifting off into intergalactic space. Others lose energy and spiral inward, falling toward the supermassive black hole at the galactic center. The galaxy does not collapse or explode. It evaporates. Star by star, remnant by remnant, the once great structure thins and disperses. The Milky Way and Andromeda, which will have merged into a single large galaxy billions of years before this point, will themselves slowly dissolve, their stellar remnants scattered into the expanding void like embers carried off by an infinite wind. The night sky, if the concept still held any meaning, would be empty. Not the relative emptiness of deep space today, where patient observation still reveals faint stars and distant galaxies. Truly empty. An observer floating in this future cosmos would see nothing in any direction. No stars, no galaxies, no nebulae. The cosmic microwave background radiation, already feeble today at 2.7 degrees above absolute zero, will have cooled to a tiny fraction of a degree, stretched to wavelengths so long they would be undetectable by any instrument we currently possess. The universe will be cold, dark, and silent, expanding endlessly into a void that grows emptier with each passing age. A darkness so complete that the concept of seeing, of light, of looking, becomes meaningless. And in this darkness, the white dwarfs will continue their work. The same work they're doing right now. The work they have been doing since the first ones formed over 12 billion years ago. They will radiate, slowly, faintly, grudgingly, each one shedding its stored thermal energy photon by photon, degree by degree, following the same cooling curve we explored earlier. The curve that decelerates at every stage, stretching and flattening toward an endpoint it approaches with infinite patience. And at some point, after a span of time so vast that even the 100 trillion year stelliferous era looks like a brief opening prelude, the oldest white dwarfs will finally reach thermal equilibrium with the universe around them. Their surface temperatures will match the background temperature of the cosmos. They will absorb exactly as much energy from the ambient radiation as they emit. The net heat flow will drop to zero. And in that moment, after a wait of at least a quadrillion years, and possibly far longer, the first black dwarf will exist. What would it be like? What kind of object would you find if you could somehow travel to this impossibly distant future and locate one of these cold, dark relics? A black dwarf would be roughly the size of Earth, its diameter somewhere in the range of 7,000 to 14,000 miles, depending on mass. It would contain roughly 1/2 to 8/10 the mass of the Sun, all compressed into this Earth-sized volume by the same electron degeneracy pressure that held it up as a white dwarf. That pressure is independent of temperature. It will continue to support the star, whether the interior is at 50,000 degrees or at absolute zero. The black dwarf will not collapse. It will simply sit, structurally stable, quantum mechanically supported, inert. Its interior would be a crystal, a lattice of carbon and oxygen ions locked in rigid geometric positions, surrounded by a sea of degenerate electrons. The crystallization that began billions of years earlier during the white dwarf phase would be complete. The entire core would be solidified. The crystallization that began billions of years earlier during the white dwarf phase would be complete. The entire core would be solidified into a lattice of extraordinary rigidity. Every ion locked permanently in place, surrounded by a sea of degenerate electrons that will never again carry thermal energy outward. It is the most ordered, most inert, most finished object the universe can produce, a dead star reduced to geometry. Its surface temperature would be indistinguishable from the background temperature of the universe, perhaps a fraction of a degree above absolute zero, perhaps effectively at absolute zero for all practical purposes, depending on how far in the future we are looking. It would emit no visible light, no infrared, no radio waves of any detectable intensity. It would be, in every observational sense, invisible. Even if you were floating within a few thousand miles of it, you would not see it. You would not feel its heat. You could detect its gravity, the gravitational pull of a roughly sun-mass object in a roughly Earth-sized volume, but you could not see it or sense its radiation. It would be a dark sphere of crystallized stellar ash, cold and silent, drifting through an equally cold and silent cosmos. And there would be many of them, billions upon billions. Every white dwarf in every galaxy will eventually reach this state. The Milky Way alone contains an estimated 10 billion white dwarfs. Every one of them is on this trajectory. Every one of them will, given sufficient time, become a black dwarf. In the deep future, the universe will be populated by trillions of these dark relics, scattered across the expanding void, each one a tombstone marking the place where a star once shone. But the story of the black dwarf may not end there. In the year 2020, a theoretical physicist named Matt Kaplan published a paper that asked a remarkable question. What happens to a black dwarf over timescales even longer than the cooling time? What happens when you wait not just a quadrillion years, but 10 to the 1100th years? A number so large that writing it out would require a 1 followed by 1100 zeros. A number so far beyond human comprehension that calling it astronomical would be an understatement of a scale that language cannot accommodate. Kaplan's paper explored a process called pick-no-nuclear fusion. This is a form of nuclear fusion driven not by thermal energy, not by the heat and pressure that powers normal stars, but by quantum tunneling. In quantum mechanics, particles are not confined to their classical positions. They have a probability, vanishingly small but never zero, of appearing in locations that classical physics says they cannot reach. A particle trapped behind an energy barrier has a tiny chance of spontaneously appearing on the other side. This is quantum tunneling, and it is a well-established, experimentally verified phenomenon. It is real. It happens constantly at the subatomic level. It is the mechanism behind radioactive decay. It is the reason the sun can fuse hydrogen at all, since the thermal energy in the sun's core is actually insufficient to overcome the Coulomb barrier between protons by classical means alone. The sun burns because of quantum tunneling. Every star in the sky shines partly because of this effect. Inside a black dwarf, the carbon and oxygen nuclei are locked in their crystalline lattice positions. They do not have the thermal energy to overcome the Coulomb barrier between them, the electrostatic repulsion that prevents positively charged nuclei from getting close enough to fuse. Under normal circumstances, fusion requires temperatures of millions or billions of degrees to slam nuclei together hard enough to overcome this barrier. A black dwarf, at nearly absolute zero, has none of that energy. Classical physics says fusion is impossible, but quantum mechanics says otherwise. Given enough time, an almost incomprehensible amount of time, quantum tunneling will occasionally allow two neighboring nuclei to fuse. Not because they have the energy to do so, but because the wave function of each nucleus extends slightly beyond its classical boundary. And once in an immeasurably rare while, two wave functions overlap at the same point. A fusion reaction occurs, not driven by heat, driven by probability, driven by the simple, patient mathematics of quantum mechanics acting over timescales that dwarf anything we have discussed so far. The fusion proceeds through a chain that gradually converts the carbon and oxygen into heavier elements. Each step releases a tiny amount of energy, but the timescales between successive reactions are staggering. A single tunneling fusion event in a black dwarf might occur once every span of time that makes the cooling era seem brief by comparison. And then the product of that reaction sits in the lattice, waiting for the next tunneling event, which might not occur for another similarly immense interval. The process inches forward with a patience that redefines the word. Over time, measured in spans that make the cooling time look brief, the composition of the black dwarf's interior slowly shifts. Carbon becomes sodium. Sodium becomes magnesium. Step by step, nucleus by nucleus, the quantum tunneling reactions creep up the periodic table. And the endpoint of this process, the most stable nuclear configuration, the lowest energy state that the nuclei are slowly tunneling toward, is iron 56. Iron is the most tightly bound nucleus in nature. It sits at the very peak of the nuclear binding energy curve. Fusing elements lighter than iron releases energy. Fusing elements heavier than iron absorbs them. Iron is the end of the line, the same element that ended the lives of massive stars, triggering core collapse supernovae when their cores filled with iron, will be the element that accumulates in the heart of a black dwarf over almost unimaginable timescales. The universe's first chapter ended with iron at the centers of dying massive stars. Its last chapter will end with iron too. The symmetry is haunting. Kaplan calculated that for the most massive black dwarfs, those near the Chandrasekhar limit of 1.4 solar masses, the accumulation of iron in the core could eventually trigger a catastrophic event. As the iron core grows, it approaches a critical mass. The electron degeneracy pressure that has supported the black dwarf for all this time has a limit. If the iron core exceeds the Chandrasekhar mass, the electrons can no longer hold it up. The core collapses, and the black dwarf explodes. This would be a Type 1a supernova. The same kind of explosion that occurs today when a white dwarf in a binary system accretes enough matter from a companion star to exceed the mass limit. But in this case, there is no companion. There is no accretion. The mass limit is exceeded from within by the slow, relentless, quantum mechanical conversion of the black dwarf's own interior into iron. The explosion will be powered by the same physics as a modern Type 1a supernova, a thermonuclear detonation that tears the star apart, converting a significant fraction of its mass into radioactive nickel 56 and iron 56, releasing a burst of energy that, for a brief moment, blazes against the otherwise total darkness of the far future cosmos. Picture that for a moment. A universe that has been dark for ages beyond description. No stars, no galaxies, no light of any kind. And then, without warning, a flash. A single point of light erupting in the void as a dead star, cold for longer than any current time scale can describe, suddenly and violently detonates. For a few weeks, it would shine with the luminosity of billions of suns, visible across enormous distances, a solitary beacon in an otherwise utterly lifeless cosmos. And then it would fade. The debris would expand and cool. The light would disperse, and the darkness would close back in, perhaps forever, perhaps until the next one, somewhere else in the void, ages later. These would be the last supernova in the history of the universe, not driven by stellar evolution, not triggered by mass transfer in a binary system, triggered by quantum tunneling acting over timescales of 10 to the 1100th years or longer. the last bright events in a cosmos that has been dark for ages beyond description. You could call them the iron supernova, a name that captures both the physics and the poetry. The final fireworks. Not all black dwarfs would explode, only the most massive ones. Those closest to the Chandrasekhar limit would accumulate enough iron to trigger collapse. Less massive black dwarfs would undergo some pycno-nuclear fusion, but their iron cores would never grow large enough to become unstable. They would simply continue to exist. Their compositions slowly shifting, but their structures remaining stable, drifting through the void essentially forever, or at least until the next process claims them. That next process, if it occurs, is proton decay. The standard model of particle physics does not predict proton decay. In the standard model, protons are stable, they last forever. But several extensions of the standard model, grand unified theories that attempt to merge the strong, weak, and electromagnetic forces into a single framework, predict that protons are not truly stable. They merely have extraordinarily long half-lives, perhaps on the order of 10 to the 40th years or longer. If protons decay, then over sufficiently long timescales, the matter that makes up black dwarfs, the carbon, the oxygen, the iron, will gradually dissolve. Protons and neutrons will decay into lighter particles, positrons and pions, which will in turn annihilate or decay into photons and neutrinos. The black dwarf would slowly evaporate, not through heat loss, but through the fundamental instability of the matter itself. Over timescales of perhaps 10 to the 45th years, the black dwarf would gradually dissolve into a faint mist of radiation and ghostly particles, leaving nothing behind. If proton decay does not occur, the black dwarfs could persist for even longer. They would be among the last recognizable structures in the universe, outlasting even black holes. Black holes, despite their fearsome reputation, are not eternal. Stephen Hawking showed in 1974 that black holes emit radiation through a quantum process, now called Hawking radiation. This radiation is incredibly faint for large black holes. A black hole with the mass of the Sun would have a temperature far below the current cosmic background, and would actually be absorbing more energy than it emits. But as the universe expands and the background temperature drops, eventually all black holes will be warmer than their surroundings. They will begin to lose mass. The process is extraordinarily slow. A solar mass black hole would take roughly 10 to the 67th years to evaporate completely. A supermassive black hole, millions or billions of solar masses, might take 10 to the 100th years. But eventually, every black hole in the universe will evaporate in a final burst of Hawking radiation, leaving nothing behind. If proton decay occurs, black dwarfs will dissolve before the largest black holes evaporate. If proton decay does not occur, then the black dwarfs might be the very last macroscopic objects in the cosmos. The final structures. The last things you could point to and say, that is an object. That is a thing with mass and volume and a surface. Everything else, the stars, the planets, the galaxies, the nebulae, the black holes, all of it would be gone. Only the black dwarfs would remain, cold crystals drifting in an infinite void, monuments to an era of light and warmth that ended so long ago that the time elapsed since would require numbers with hundreds or thousands of digits to express. And eventually, even they would be gone. Whether through proton decay or through the iron supernova mechanism Kaplan described, or through some process we have not yet imagined, the black dwarfs will not last forever. Nothing material lasts forever. The universe tends toward equilibrium, toward uniformity, toward a state where no gradients exist, where no energy is available to do work, where nothing changes, nothing moves, nothing happens. This is the heat death of the universe. The final state predicted by the second law of thermodynamics. Not a dramatic ending, not a cataclysm, not a bang or a crunch or a tear. Just a slow, quiet, irreversible settling into permanent equilibrium. The temperature everywhere approaches absolute zero. The density of matter approaches zero as the universe expands without limit. No structures remain, no energy flows, no processes operate, no information is exchanged. The cosmos becomes a vast, cold, empty, featureless void, expanding forever into nothing, with no prospect of change, not merely dark, not merely cold, but thermodynamically dead, incapable of producing any event, any interaction, any phenomenon of any kind. The universe does not end in the heat death. It continues. It simply has nothing left to do. Time passes, if passing is even the right word, when nothing distinguishes one moment from the next, and nothing ever happens again. The black dwarf is the last signpost on the road to this ending. It is the final recognizable structure the cosmos will produce. After the stars have burned out, after the galaxies have gone dark, after the neutron stars have cooled and the black holes have evaporated, the black dwarf remains. Cold, dark, patient. The last physical object in a universe that once blazed with the light of 2 trillion galaxies. And when the black dwarfs are finally gone, consumed by iron supernova or dissolved by proton decay, or simply waiting in the dark for the end of time itself, there will be nothing left to mark that the universe was ever anything other than empty. Think about the strangeness of that for a moment. Right now, tonight, the black dwarf exists in only one place in the entire universe. Not in space, not in any galaxy or cluster or void. It exists in the minds of the beings who calculated it. It exists in equations written on whiteboards, and in simulations running on computers, and in the understanding of anyone who has followed the logic from white dwarf to cooling curve to crystallization to the impossibly long wait. The black dwarf is real in the way that a mathematical proof is real. It is certain. It is inevitable. But it has no physical presence anywhere. It is an object that lives for now entirely in thought. And there is something extraordinary about that. Somewhere in this vast, cold, expanding universe, on a small rocky planet orbiting an ordinary star in the quiet suburbs of an ordinary galaxy, conscious beings figured out what will happen to dead stars in a future so distant that no word in any human language was designed to describe it. No one asked us to do this. No survival pressure demanded it. No predator required that we understand white dwarf cooling curves. We did it because we are the kind of creature that looks at the universe and wants to know what happens next, even when next is a quadrillion years away. And consider this. The era we live in, the stelliferous era, the age of stars and warmth and light, is not the default state of the universe. It is the exception. If you could somehow sample a random moment from the full timeline of the cosmos, from its beginning to its inconceivably distant future, the overwhelming probability is that you would land in darkness, in cold, in silence. You would find yourself in an era with no stars, no galaxies, no light of any kind, just black dwarfs and the void. The age of warmth is the anomaly. The age of darkness is the norm. We happen to exist during the brief, bright, improbable window when the universe is doing something interesting. When matter is organized into structures that burn and shine and produce the conditions under which complexity can arise. This window will close. It is already closing, slowly, as the rate of star formation declines and the fuel supply dwindles. But it has not closed yet, and we are here, awake, aware, looking out at the cosmos during the one era when there was something to see. That knowledge does not diminish the present. If anything, it sharpens it. Knowing that the warmth is temporary makes the warmth more precious, not less. Knowing that the stars will eventually die makes their current burning more remarkable, not more routine. Knowing that the cosmos will one day be populated by nothing but cold, dark, silent crystals drifting through an infinite void makes this moment, this era of light and heat and life and consciousness, stand out against the darkness like a single candle in a cathedral that stretches beyond sight in every direction. The candle will go out, but right now, it burns. And it is beautiful precisely because it will not burn forever. This is what the Black Dwarf teaches us. Not just a lesson about stellar remnants or thermodynamics or quantum mechanics. Though it teaches us all of those things, it teaches us something about time, about how much of it there is, about how little of it we occupy. We live in the first fraction of a percent of the universe's total history. The stars that fill our sky, the warmth that sustains our lives, the light that lets us see, all of it is temporary. A brief, brilliant flash in what will be an almost endless darkness. The universe is too young to have made a black dwarf, and that single fact tells us everything we need to know about where we stand in the story. We're at the beginning. The very beginning. The cosmos is still warm, still bright, still churning with activity and energy and light. Stars are being born right now in nebulae across the galaxy. New planets are forming. The universe is alive in a way that it will not always be. And the black dwarf, cold and dark and impossibly patient, is the reminder that this aliveness is not permanent. That the warmth will fade. That the light will go out, that the cosmos will cool and darken and empty, until all that remains are silent crystals drifting through an infinite void, carrying within their frozen lattices the memory of a time when the universe was young enough to burn. No black dwarf exists yet. The universe has not earned one. But every white dwarf in every galaxy is cooling toward that end. One photon at a time, 1 degree at a time, on a journey so long that the destination lies beyond the reach of any imagination. And the fact that we can know this, that we can calculate it, that we can sit on a small rocky planet, orbiting an ordinary star, and deduce the fate of objects that will not exist for ages beyond ages, that is perhaps the most remarkable thing of all. We are brief, we are small, we live in the opening moment of a cosmos that will last for stretches of time that have no name. But we can see the ending from here. We cannot visit it. We will never witness it. But we can describe it with precision, with mathematics, with the quiet certainty of physics. And in doing so, we make the black dwarf real in the only way it can be real right now. Not as an object in the sky, but as an idea in a mind. A prediction written in the language of the universe. A certainty waiting, with infinite patience, for the cosmos to catch up. Thank you for joining me on this journey. If this exploration meant something to you, a like or subscribe helps more than you know. The universe is vast and dark and full of time. And tonight, you know a little more about what is waiting in that darkness. Sleep well, knowing that the stars are still burning, that the light is still here, and that the cosmos, young as it is, has a very long way to go before the first black dwarf finally takes its place in the silence.